Hi there! So, in this video the goal will be to calculate the gradient of the loss function we introduced in the first video with respect to the parameters of the last layer. So specifically with respect to the parameters w, l-1, or the ijth parameter in that weight matrix, and the ith parameter of our bias vector. So these are the parameters, and the values you want to compute are the partials of the loss function with respect to, well, each of those parameters. And remember that here I'm using the notation I introduced in the last video. So we are differentiating the loss function here with respect to this variable, and then this variable in our Python code, this variable will actually be just a real value, which we will plug into the differential of this loss function. And the other thing to remember is that the loss function here is just, well, it's hiding notation. There are inner arguments that I have omitted here in this notation. So one thing to remember is that the loss function here was, when I write the full notation here, was defined as the loss of the neural net of x and y, which we had defined as the other loss function of nn of x, which we have also called y hat, and our y, which I can further unpack the notation because we had defined neural net as a tuple of parameters and hyperparameters. So I can also write the loss of fl, and then inside here we had the argument wl-1 times al-1 plus the bias bl-1. And then notice that the al-1 also decomposes into the previous arguments, but for now this is as deep as we will unpack this expression here, because when differentiating with respect to some parameters, as we have done here, as soon as the indices appear here when we unpack the notation, we have unpacked enough in order to be able to calculate the gradients. So the other argument was y. And so we want to differentiate this with respect to, well, either one argument here in the weight matrix or another argument in the bias here. Okay, so that's what we will do in this video. So then, first let me unpack this. Then we get this here and y. Now we can apply the multidimensional chain rule onto this term. So we have two Jacobian matrices that result from that, which are the differential of this with respect to y hat multiplied with the differential of y hat with respect to w-l-1 plus, and now the first argument is the same thing, but we differentiate it with respect to y instead of y hat, and we multiply it with this here. And now notice that this expression here already must be 0 because y doesn't depend on this parameter, which we can see if we look at the formula here. So the weights and biases, they appear in this expression here, which then further makes up the left argument of our loss function, but they never influence the actual target, which makes sense, right? We have a fixed data set, so the target should not depend on our neural network. So this here is 0, which means that the entire second expression just vanishes. So then let me unpack a bit further. So we have this here times this, and now I will unpack the y hat. The thing that comes previously is fl of zl-1, and now I can differentiate this expression with respect to zl-1 and then multiply it with the differential of zl-1 with respect to the parameter. And now let's look at the dimensions of these things here. So this here should be just a single number, because this here doesn't have any component. The result of this function here is just a single scalar value, and here we only have one parameter. So we input one parameter and we output one value, which means that the Jacobian matrix here should really just be a 1-by-1 matrix, so just one value. But the matrices we get in between here, they are not 1-by-1 matrices, but their dot product is at the end. So then let's think about the shapes of these matrices. So first we have a Jacobian matrix that looks very much like this, because we have multiple input variables, but we only have one output value. So we don't have component functions, which is why we only have one row, but we have multiple columns for all of the input variables. Then we apply a function f here to our value zl-1. Fl-1 doesn't change the dimension, which means that we have as many inputs as outputs, which means that this Jacobian matrix here is a square matrix. And square matrix have the property that they don't change the shape of the matrix they get multiplied with. So if we multiply these two together, we get a matrix that has exactly this shape here. And now finally, we have this expression here, and here it's the exact opposite case as here, because we have multiple component functions, but we only differentiate with respect to one variable, which means that the result must be shaped something like this, where we have each component here in the rows, but only one column for the variable. And now when we multiply all of these matrices together, then this here kind of doesn't matter anymore. And then something with this shape times this is just a dot product between two vectors, which leaves us with exactly one scalar value. Okay, so something that is 1 by 1. Okay, so let's go through the same calculation with the bias. So the derivative of the loss with respect to the last layer bias, or one parameter of that bias vector. Okay, now honestly, I don't want to do the same calculation again, because it is really extremely similar. If we think about what happens when we unpack the chain, then we get pretty much the same expression, except for the last term, right? So only here, when we have unpacked it this far, is where we see a change, because these values here, they don't depend on whether we differentiate with respect to the weight or the bias. It only matters that we unpack in order to get to the ZL-1, because the ZL-1 contains, as we see here, both the weight matrix and the bias vector. So we unpack the loss to the same deepness. So as I said, I can basically just copy this expression here and then replace the last W here with the bias. And so that's what we get. And so this will be a common theme when applying the chain rule, that the first expressions always will be the same, whereas only the last one will either be a weight, a bias, or another thing we have to unpack. And so this is why I want to introduce notation that will abbreviate all of the first components of our derivative chain. So what I mean by that is that these two terms here, I will abbreviate them with this little symbol here. So delta L-1. And so delta L-1 is a matrix of that shape here. And with this little delta symbol, I can abbreviate both expressions as delta M-1 times the last thing here. So this is for the bias, and this here will be the formula for the weight. Okay, so now in theory, we would be done with the calculation of the gradient of the loss function with respect to the last layer parameters. However, if we were to leave it like that, we would get bad Python code. And to show you why, I will write a gradient descent step in pseudocode now. So the gradient descent step, so in one step, we would have to loop over the i's. Now I is the number of rows we have, and the number of rows determine the output dimension, so it's dl. And so for every I, we would then have to loop through every j from 1 to the input dimension, dl-1. And then in each loop iteration, we would have to calculate the number we just computed here, which I will call, I don't know, gradient, g, value, and then I don't know, that's some computation here, which I'm not going to write down. And then we would have to update our weights and biases, right? So remember that all of our weights and biases were stored in Python lists. So we would have to get the correct index. So first we access the last weight matrix, and then we access the ith row, and then the jth column. And then we update it by setting it to itself minus the learning rate times the gradient value we just computed. Now the learning rate determines how big the steps are that we make during our backpropagation, and the bigger learning rate means that we take bigger steps, which means that, well, this is good if we are not very optimized, but as we get closer to a minimum, we want to reduce our step size, because if the step size is too large, then we could also just step out of our local minimum and never converge to any meaningful value. But again, that's a hyperparameter here, which we will not further discuss right now. And this is not very beautiful. What we would like instead is to define a gradient matrix. So d, w, and then L-1 here, which contains all of the gradient values I and j, right? So this here will also be a matrix. We will compute it with some calculation here. And then for the gradient descent step, instead of looping through i's and j's, we can just write w l minus 1 is the same as, well, first itself, and then we subtract the learning rate times this gradient matrix. And for the bias, we would do the exact same. Instead of iterating through each of the bias values individually, we just gather all of the gradient values in a vector and we subtract the vector from the original bias. Okay, so with that motivation, let's define our dwl-1. So we have said we want to gather all of the individual gradients in a matrix. And so the mathematical way of writing it down, I think, would be something like this. So we have the matrix, where in each entry we have this value here. So let's think about how, what this looks like. So we had our delta L minus 1 times this value here. Okay, and so now the only thing left to do is to do a calculation on this value here. So let's unpack the z L minus 1. So what we have here is w L minus 1 a L minus 1 times plus the bias L minus 1, and we differentiate that with respect to this parameter. And now this here again is a Jacobian matrix, which is a long column vector, right? Because we only have one variable but multiple component functions here. Now there's a neat way to split up this vector into its multiple component more explicitly, and this is where unit vectors will come in handy. So I can just write this as a sum from 1 to dl, because dl is the number of entries we have, and this little e hat and k signifies that I mean the kth unit vector. And in case you don't know what that is, that's just a vector which has 0 in all entries except 1 in the kth entry, and yeah, that's it. Kth row. Okay, and so if I multiply the unit vector with some scalar and then take the sum over all of the unit vectors, then I can write down the vector with multiple components. Okay, but then let's think about the actual entries of our Jacobian vector. If we take the kth component of this vector here, then what we get is, well, first here we get the kth component of our bias, and we add the result of this matrix multiplication, and from here only the kth component, which we get by taking the kth row of the matrix here, multiplied with all of the values of A, and then taking their sum, right? So we can write this as a sum from L going from 1 to the number of columns that we have, which is dl minus 1. Then we take the kth row and all of the column entries. We multiply it by a L minus 1, all of its entries, and then we add the kth bias term. And now we have broken it down so far that we can actually see what the gradient should be, right? So we can pull in the gradient into the sum here, and we can also pull it in front of the bias. But of course, when we differentiate some parameter, let's call it x, with respect to some parameter which is completely different, then we just get 0. It's only when we derive an expression that actually contains the parameter that we get something that's non-zero. So the only case we get something that's non-zero from this expression here is if the ij indices are the same as k and l. In all other cases, the derivative is just 0, because this variable is a different variable than all of the others here. Okay, so knowing that, we can write down two conditions that have to be met. The first condition is that I is equal to k, and the second condition is that j is equal to l. And I hope you have already seen these Kronecker delta symbols. These are functions which take the indices as input space and output 0 or 1. And more specifically, they output 0 every time the two indices are different, and 1 every time they are different. So these are really they just exist to make notation simpler. And so our two conditions are that I is equal to k, and the second condition is that j is equal to l, which gives us these two deltas. And in case these conditions have been met, the actual derivative we get here is just a L minus 1, because we are differentiating x times y with respect to x, so don't forget the delts here, and this just returns y. And so we are left with a L minus 1. Okay, and now we can simplify this last time, because if we know that k is equal to I, then all of the other unit vectors just vanish. They get multiplied with 0. So the ith unit vector is the only one that survives. And here it's the same. Well, honestly, I should have written a sum over all of the L's, but they all get to 0 except for when L is equal to J, which means that we are only left with a J L minus 1. Alright, and so this is the expression we can use now to calculate what goes in here. So we get delta L minus 1 times, so we had the ith unit vector times a L minus 1 J. And then we take the matrix. Okay, but we can further simplify this, because in our case here we're taking a dot product of the delta with a unit vector. But note that only the ith component here is non-zero, and it is also 1, which is very specific, because that basically pulls out the ith component of whatever we multiply it with, because all of the other components, they get multiplied with 0. So we are left with the ith component of our delta, and don't forget the scalar here, a L minus 1. And so that's what we are left with. And now we can simplify it one last time, because what we are looking at here is exactly what we would also have gotten if we had taken the outer product of these two vectors here. So let me write down the term first. Okay, so let's think about that. This first vector here, we transpose something that is a row vector into a column vector. And here we transpose a column vector into a row vector. So what happens if we take their outer product? Well, let me write it like this. And then imagine here are some parameter values. And what we get then is a matrix which has this value here times this value in this component, then this times this in this component, this times this in this component, etc. So now the only thing left to verify is that the indices I and j really match up. The index I refers to the row and the index j refers to the column. So if we, look at this combination here, then we have I equals 1 and j equals 2, which means that the indices of our first vector, they make up the i's, whereas the indices of our second vector make up the j's. And so this is exactly what we have right here. This here makes up the i's, and these here the j's. So this must be the column vector, and this must be the row vector of our outer product. This is why we have to write it like this. And the alternative would have been to write it like this, a L minus 1 times the delta. This is also an outer product, but it's the transposed matrix of the one we want to get. So these are not the same. We have to pay a bit of attention, but since we are careful, this is the correct result. Okay, so now let's do the same with the bias. And we have done most of the calculation already, so this will be a lot faster. We will define dB as the gradient vector of, the gathering all of the individual gradients, and then we gather them in a column. Okay, and once again, we had written it down as delta L minus 1 times the derivative of z L minus 1 with respect to the bias. And now I want to go back to this calculation here, because the only thing that changes from W to B is this term here. So if we were to unpack it, we would get the same as here, except that we would have the bias here in the denominator. We would do the same notational trick here, and once again, the only difference would be that here would be the bias. But now let's think about what happens to this expression here if we differentiate with respect to the bias instead of the weight. And the effect is that all of these values here go to 0, right? Because the parameter only matches the expression in the top if k is equal to I. And in this case, we have that we differentiate the variable with respect to itself, which gives us 1. And all of the other terms here, they vanish because they don't depend on the bias. So let me recap that. This here gives us the sum of all of the unit vectors from k equals 1 to dl. And then we had two conditions. First, that k is equal to I, which gives us delta ki. And then the result of our differential is just 1, because we differentiate the variable with respect to itself. So this gives us 1. But we can further simplify this. If we know that k is equal to I, then the ith unit vector is the only one that survives. the scalar factor of 1 just doesn't matter. Okay, so we can write this entire expression here as, oh sorry, I forgot the I here. The entire expression as delta L minus 1 multiplied with the ith unit vector, which is the same as pulling out the ith component here of our delta as before. And now what we are doing here, this expression is just a column vector which gathers all of the entries of delta L minus 1 in their individual entries. And so the resulting column vector is just the same as if we had transposed our row vector delta L minus 1. And so now we're done. We have calculated dW L minus 1 and dB L minus 1, which gather all of the gradients into one matrix or one column vector. So in the next video, I will do the same calculation for all of the other parameters and also gather them in columns and matrices. And so I hope I see you in that video. Bye!